like studying physics because it gives me a deeper understanding of the world.
Hi, I'm Christy. I'm a freshman at Carleton, and I like studying physics because I'm hoping to be an engineer.
In this video, we're going to explore Newton's third law and the way in which it relates to kinematics, momentum, and energy.
We're going to be looking at a certain type of collision using the most frictionless environment that we have available to us, which would be an ice rink. So what we're going to do is we're going to take our momentum equations because we know that if Newton's third law holds true, the initial momentum has to equal the final momentum. So we are going to evaluate our equations for the situation that we choose. And if we're given Marco's mass and both of our velocities, we should actually be able to calculate my mass. Once we do that, we'll know that the third law holds, and we can evaluate the situation for energy as well. In order to start talking about Newton's third law, we have to first understand what an interaction is. So all forces are interactions. When you have A pushing on B, then B is also pushing back on A, and that embodies what Newton's third law is.
In order to better understand Newton's third law, allow me to propose an example.
Okay, so in the situation that you have just observed, we know that we have something called an explosion, which is where two objects start at rest together, and they have a brief, intense interaction with a force that makes them push away from each other. So in this type of situation, we know that momentum and energy must be conserved if we want Newton's third law to hold true.
As you saw in the video, if you look at the video, Christy moved 1.93 meters to the right, and I moved 1.625 meters to the left. If you look at the equation for conservation of momentum, you get that initial momentum has to equal final momentum. Our initial momentum was 0, since we were at rest. Our final momentum will be Christy's momentum plus my momentum. Christy was moving to the right, so her momentum is positive. I was moving to the left, so my momentum is negative. In order to simplify these equations, we're going to take our distances traveled and substitute these for our velocities. Since velocity is distance over time, after a certain period of time, we will have traveled proportional distances to our velocities. Now let's solve the equation to get one of our masses. Christy's mass should equal my mass, which is 130 pounds, times the distance I traveled, which is 1.625 meters, over the distance that Christy traveled, which is 1.930 meters. When we plug these equations into a calculator, we get that Christy's mass equals 109.46 pounds. When in fact Christy's actual mass is 113 pounds. Do we think this is reasonable?
So now we can also use Newton's third law to figure out the energy of the explosion. So we know that energy is conserved in Newton's third law. So energy initial equals energy final. And all the energy in this situation is kinetic. So we calculate Marco's energy, which is 1/2 of his mass times velocity squared, then my energy, which is 1/2 of my mass times velocity squared, and we add them together, and we get a total of 21.44 joules for this explosion. Now that you know about Newton's third law and the way that it holds true for everyday situations, let's kick things up a notch. Imagine this situation. So, you have a particle and it explodes into 3 equal pieces. The energy of the explosion is 245 joules. And the original particle is 0.009 kilograms. Can you find the velocity of each new piece of the particle as it explodes? Use Newton's third law, and here's a hint: you may want to extrapolate from the momentum and/or the energy equations.
Thanks for watching. We hope you can use this information to expand your understanding of the world. We hope you have fun in physics, and have a great year.